Yeah, I guess we can slowly start. So welcome to the third part, and yeah, Ryan, please.
Okay, sure. Yeah, I just ate my lunch super quickly, so I apologize. I will try my best not to burp into the microphone directly. I just like wolf down lunch. Yeah, like a wolf. Okay. Um, right. So now we're going to talk about possible pathways to lower balance. Well, I've mentioned a few off and on, but this is the most recent work that we've been doing. So as you have probably surmised from the previous 2 hours, lower bounds are hard to prove. That's kind of the one fact we know very well about lower bounds is they're going to be hard for us to prove. We don't know a great deal of them, but we know they're going to be hard. There's many barriers, which you have seen, showing the standard methods we use to reason about generic computation cannot resolve P versus NP, and a host of other problems involving complexity classes. So we know a lot, it seems, about what strong lower bounds cannot look like. Lots of limitations. And so the next question, well, the real question we'd like to know is what could a proof of P from NP look like? We know lots of conditions, they cannot relativize, they cannot even, algebraize, they cannot naturalize, they cannot have embedded in them some algorithm that allows you to distinguish um, random from easy and so on. So can we identify properties that such lower bound proofs must possess? Like some just consequence of the lower bound holding that must also be true. On top of that. So another way of saying it is what properties are missing from lower bounds we know how to prove, which we will have to include in a proof of, say, non-deterministic exponential time is different from randomized polynomial time, okay, or any of the above things. So what are the missing ingredients in our lower bound toolkit? And so our recent work is trying to provide some kind of answer in which algorithms have to be central to resolving major lower bound questions. Okay. So to get a handle on this question, what could a proof look like? Let's look carefully at what it means to prove a lower bound. So if I have like some function, let me try to get my laser pointer here. Okay, yeah, laser pointer. So if I have some function, a decision problem, and some class of algorithms a lower bound saying it's not in the class of algorithms A, it's a claim of the form for every algorithm in the class, for infinitely many n, there is a bad input. There is some input of length n on which the algorithm gives a different answer from the function, right? And we need to have infinitely many for most models just because if there are only finitely many bad counterexamples we could come up with, we could have some larger code which has these finitely many examples hard-coded in them. Just it covers those like with some lookup table. Okay. So for every algorithm A, someone has to respond with a bad input X that confounds the algorithm A with respect to this function. All right. So the question is, we're looking at fix a lower bound problem. So the problem of proving some F is not in some class A, and fix an algorithm A from that class. So what is the complexity of constructing this bad input? This thing which has got to exist for infinitely many input lengths. Okay. Now, the literature on lower bounds gives roughly two types of answers to this question. Okay. One answer is that you choose random ways of picking the input or some non-constructive way of choosing the input. And these often arise from proofs that rely on counting or information theoretic arguments. So proofs that rely on communication, complexity, various proofs of time-space lower bounds for explicit problems in P. They work by choosing some random X sub A from some distribution and arguing that the randomness in the string can fool the algorithm A into making a mistake. And so this is one popular way of just constructing bad inputs, picking them at random in some way. The second class is that of efficient ways of choosing exobay. Okay, and this often comes from proofs based on diagonalization arguments. And actually, I don't really know of lower bounds that aren't somehow diagonalization based arguments that have efficient ways of choosing bad inputs. So the canonical example of class 2 is the standard proof by diagonalization that the halting problem is undecidable. So given the code of a Turing machine that purports to solve the halting problem, you can effectively produce a bad input in which that program fails to correctly decide halting. This is like something you can do just from massaging the proof the halting problem is undecidable. Okay, so there have been efficient ways of choosing bad inputs for very old arguments, and the idea of focusing on bad inputs when thinking about lower bounds is also very old. So for one more example, the Myhill-Nerode theorem from the 1950s says that a language is non-regular if and only if there's an infinite set of bad strings. And effectively, this bad string set forces every possible DFA to need infinitely many states because it's an infinite set of bad. And sort of like each new string in your set is forcing a new state in your DFA. And because you have an infinite set, you need infinitely many states, so there cannot be a deterministic finite automaton, right? So this is like the two kinds of answers you get for the complexity of constructing bad inputs. And so our starting point is from this beautiful paper of Gutfreund, Schaltel, and Toshma from 2005, which effectively says if P is in from NP, then bad inputs to SAT algorithm. Okay, so just assuming P is from NP, there is a way to construct bad inputs. All right. So the following theorem can be derived from their paper, and I'll say at a high level, I guess on the next slide, how it works. So for every end of the k time algorithm A, so fix some constant k, it's running in the k time, there is a refuter algorithm, R sub A, that for infinitely many n, R sub A, just given the string of n ones, it outputs a bad formula. It outputs a formula so that this formula is satisfiable if and only if the algorithm actually outputs 0, like declares unsatisfiable. Okay, and furthermore, this R sub A runs slightly larger, but still polynomial time to the order n in the k time. All right. So for every polytime algorithm, there is some refuter running in polynomial time, which if you give it some input length, it will print a bad formula on infinitely many n. It will print something which kind of witnesses the failure of this algorithm to solve the SAT problem. Okay. Right, so yeah, so this is called a refuter. This terminology originally, I guess, is from Kabinetz, who was looking at de-randomization against polynomial time algorithms that construct inputs. Okay, so let me kind of give the ideas behind this Gutfreund, Schaltel, and Toshma papers. It's very important to what we're doing. So the idea is, okay, let's start by trying to get a refuter for an end of the k time algorithm A that's trying to print satisfying assignments. So instead of trying to decide satisfiability, we are going to look at algorithms which are actually printing satisfying assignments when they exist. Okay, so it's going to just print something. So such algorithms will always output unsat if it fails to satisfy, right? It will print something, then we can just check its answer, right? Because it's NP. We can just check whether the thing actually works. So all the bad inputs, right? If it checks itself and makes sure that an assignment is satisfying before it gives it, all the bad inputs will be satisfiable formulas on which it outputs unsat. Right? If it's unsat, it will never output sat because it's trying to find a satisfying assignment and checks that it works. So then all the bad inputs will have to be satisfiable formulas, but this algorithm says nope, it's unsat. Right? Okay. All right. So how do we get a refuter for this thing? It's a slightly easier way to think about it. Like, so instead of deciding sat, you're trying to you got a SAT solver or something attempting to actually print a SAT assignment. So here's the the trippy idea. Okay, you construct a formula that asks the algorithm to find its own counterexample. Okay, so we construct a formula f sub n that encodes the following property. Okay, there exists a formula G of length n and some assignment A, so that G outputs true on that assignment. So G is satisfiable. Nevertheless, the algorithm A on G outputs unset. Okay, so the point is, you can construct a Boolean formula encoding this property, right? You can, using the Cook-Levin theorem, right? You can cook up a Boolean formula, f sub n, encoding this property, and the size of it will be about n to the order k, right? Because our algorithm runs an n to the k time, right? I'm going to encode like the algorithm's functioning in my formula. So it'll take n to the order k size using like the standard like Cook-Levin type reduction, all right? So next thing I do is I run my algorithm on f sub n, okay? Now, because A runs an n to the k time, that's where I get n to the order k squared. I'm running an n to the k time algorithm on an input of length n to the order k, right? Now, if A prints some G, right, that's a counterexample, right? If it found a counterexample, then print it, okay? Otherwise, output the formula f sub n. Okay, so we either output the counterexample if you found one and it works. Okay, you check the satisfying assignment, the thing outputs, and then if that doesn't work, then you just print the formula which is supposed to ask it, to find a counterexample. All right. So let's think about this. So we're asking A to print its own counterexamples when we feed it f sub n, right? If it does this for infinitely many n, we are done, right? There are infinitely many input lengths for which it's printing counterexamples. Okay. If it does not do this for infinitely many n, okay, then the set of formulas f sub n is going to be printed instead, right? It's printed for almost every n, okay? But because p is different from np, f sub n must actually be satisfiable for infinitely many n. Okay, because p is different from np, this actually has a satisfying assignment, right? P is different from np, there must be infinitely many counterexamples, right? There must be infinitely many bad inputs on which this thing outputs. So that's a satisfying assignment for this thing. This will work if A is non-deterministic. No, it needs to be co-non-deterministic, because to output unsat, we need to use a universal quantifier. You gotta be a bit careful, but yeah, but it actually just breaks, I guess, unless it's an non-deterministic algorithm which just fails to solve SAT. Yeah, it's possible, right? It could just be like, I forgot to guess the satisfying assignment or something. I mean, or I guessed something wrong that didn't. It's not. Yeah, but it outputs unset, so you got to be right. Yeah, actually, if that, yeah. Anyway, that would be nice if it could work for that. But yeah, yeah. So either way, it's like a win-win argument. We don't necessarily know which is going to win out. That's based on the algorithm A itself, like whether it actually works on these formulas or not. Like if it works on the formulas, it will print counterexamples. If it doesn't work, those formulas are counterexamples. QED. That's it. That's how it goes. So you see, this is why I like this. I like this theorem very much. This is like a maybe baby version of what they're doing, but this is like the starting point. Any questions yet? We see it's like pretty trippy. It's like it uses the code of the algorithm actually to construct the formulas in the counterexample. It's kind of nice. Certainly not black box. Like it's certainly depending on A in a crucial way.
So this proof will have problems with relativization?
Oh, good question.
Yeah.
Good question. Does it relativize? Actually, I don't want to go that far and say it doesn't relativize. So yeah, but we can think about it later. But yeah, if I stick an oracle here, I need something that is solving SAT to that oracle. I mean, the way I'm looking at it, I think it would relativize, but it's but at the same time, it's non-black box. There's a slight difference between these two things. That like it does depend on the code of the thing,
But you can stick in the
I
oracle
think
because you
so.
work
Yeah,
with
I don't
machine
see.
and not circuit, right?
Yeah, right. We're not.
Yeah.
We're still like kind of, because the Cook-Levin theorem relativizes. So yeah, there's definitely a sense in which it does relativize. So yeah,
Good.
yeah. All right. So this is for like things printing satisfying assignments. Okay. How do we get something for things trying to decide set? So it just outputs set unset. This is a little trickier, but we can kind of modify what we did before. Okay. This will like so the first one is a bit simpler. So we construct the formula as before. Okay. But we only have a decider for a set. We don't have a something which is printing satisfying assignments. But okay, there's a standard way to take a decider and get a search algorithm. Use a search decision reduction that will look for a satisfying assignment. And the idea is you just plug in variables one at a time, right? You plug in x equals 0, simplify it, see what A reports. If it reports sat, you continue. If it reports unset, you stick in x equals 1. You try that one. If it says unsat for both of them, you just declare unset, right? So you kind of do these, so you do this kind of search, like you plug in variables one at a time and trying to get a satisfying assignment, okay? All right, so what are the possible cases that could happen? Well, one case is that the thing just reports unsat at the very beginning, okay? Then in that case, we just output the formula, right? And we know that if P is in from NP, this formula is actually going to be satisfiable infinitely often. Okay, so case one, we just output estimate. Okay, case two, we actually find a satisfying assignment using this search decision reduction. Okay, which we check. Okay, then in that case we output the counterexample we found. Right. The third case is that we get stuck somewhere because the algorithm is actually bad. Right. So how do we get stuck? We find some subformula by plugging things in so that it reported sat on this subformula, right? But when I plug in a variable as 0 and as 1, it says unset, right? Like, so that's the way in which it would get stuck, right? If it if it keeps saying sat at the end it says sat, then I'm fine, right? It's set. So the problem is that, like, yeah, it could get stuck because the algorithm's wrong. The algorithm doesn't always give the right answer, right? So now we have 3 formulas. So we know that, like, in case 3, this algorithm is wrong on at least one of these 3. Right, like they can't simultaneously all be true, right? Like if it's satisfiable with bit set to 0 or the bit set to 1. And so we know it's wrong on at least one of the 3. So there are various things you can do. So Gutfreund, Schaubtel, and Toshman, they just said you can report the set as bad. Like there is something in this set that's bad. Okay, but actually you can get a refuter so that only one is reported. Okay, the idea is you have like 3 different algorithms. R1, R2, R3, and in R sub I, you report the ith of these 3. Okay, and then you can just say, look, one of these has to give me counterexamples infinitely often. Okay, over infinitely many n. Okay, so there's like a trick. It's kind of funny because that's like a non-constructive trick to talk about constructivity, whatever. But okay, you can do it. All right. So. Right, so that's how it works. All right. So I think it's kind of very fundamental result. So I thought I would try to explain it here. Okay. So back to our starting point. Okay. So let's generalize what's going on in this thing. So this is saying this is some extra requirement of a P different MP proof. Not only do you have P different MP, but like there is a polytime algorithm which will print these bad examples for you, given for any particular algorithm. Okay. So let's say there's a P constructive separation proving that F is not in A. If for all algorithms, capital A, not fancy A, there's a polynomial time algorithm refuter, R sub A, which for infinitely many n, given the string of n1s, you can output this bad input. Okay, this is just kind of making a definition from a theorem that's already there, because the theorem let's just restate the theorem saying that if P is in MP, there's a P constructive separation that sat is not in P. That's what we're saying. Okay, so it's like some extra property you get from P different MP. Okay, and we want to know, like, I mean, is this some interesting property of a lower bound that we would expect to hold for other lower bounds? Like, is it like some widespread phenomena? Is it just like only because the P versus NP question? Like what would happen if I got constructive separations for lower bounds I already knew? Like you can ask all these kind of questions, right? So, so that's just the definition here again. So the question is like, which lower bound problems are going to require p-constructive, or you can have other notions of constructive separations, and which lower bounds don't. They don't require it, and in fact, making them constructive is impossible. I mean, we actually show some example in the paper where that's true. But this, I want to say, this is an algorithmic question about the nature of the lower bound, right? Like which algorithms are implied by separations. So I have a lower bound. Which algorithms can I get from it? I mean, this is something that happens like in cryptography. From lower bounds, you get nice cryptographic constructions. In de-randomization, from lower bounds, you can remove the randomness from randomized algorithms, making them deterministic. So it's like what algorithms about the separation are implied from the separation. So we argue in our paper that constructive separations are key. We're not going to say they're the key to proving major separations, some major separation lower bounds, but they're a key. They're certainly important. So we have like basically two sets of results that try to get a handle on this. So the first set is that essentially all open separation problems regarding polynomial time require constructive separation. So they will just have as a byproduct this refuter algorithm, okay? So the formal theorem, which we prove in even more generality in the paper, is that you take a class C, which is say polynomial time or some version of randomized polynomial time, and you take any class D, which is like NP, P space, exponential time, NX. There are many more in the paper. If C, the weak class, is different from D, the big class, then there is a C constructive separation showing that C is different from D. So we find some complete problem for D, and we show that there's a constructive separation that C is, that complete problem is not in D. Okay, so I'm not going to define what randomized constructive means, but it's the usual, it's the same kind of notion, except it has randomized stuck in instead of P, polynomial time. All right. So it's like for like all these different problems, okay, if we manage to prove a good separation against polynomial time, we're going to get a constructive one also, whether we like it or not. I mean, this is for NP, right? We have some way of like searching for the satisfying assignment, whatever. But for P space, for NX, things like this, it's totally not obvious how you manage to get some BPP constructive separation, like some BPP algorithm just printing bad examples for NX problem, but you can, turns out. So this is like a generalization of this GST05 paper to hold for many, many different C's and D's. Okay. So the second set of results we show shows how much more powerful constructivity is compared to other ways of proving lower bounds. So we show that making many known lower bounds constructive will actually require resolving other major lower bound problems. So recall I was talking about like there are two different types of ways of generating bad inputs. Usually you do it by like randomness or a counting argument, or you do it in some efficient way. And what we show is that for many lower bounds proved by counting arguments, making them constructive would be a major breakthrough in other lower bounds. So somehow like constructivity is like a dividing line between these kind of information theoretic lower bounds we know how to prove quite well, and like P versus NP type lower bounds we'd really like to prove. So this is, yeah.
There's a question, sorry to interrupt you. This was I guess about the first point. For all of these, is it as before and in the previous result that this is an explicit algorithm that is a refuter?
Oh, this explicit algorithm R sub A is a refuter if P is different from NP. Yeah, because in the, well, I mean, there is a step where we say like at least one of these algorithms is a refuter, but like, right, we're writing down the algorithm here. Yeah. So and I think all of these proofs, like they're uniform in the sense that like there is an algorithm that given the code, there's one algorithm that given the code of the algorithm you want to break and one to the n, it will work. It will, it will give you the bad input for that code you gave as input. So in that sense, it's pretty explicit. Yeah.
And just as before, if the separation holds, then this is actually a refuter, or it's complete
Yeah.
refuter.
Yeah, especially for the one about printing. Now, the one about deciding, right, there is this one thing where it's like, okay, one of these things is going to work, but yeah. So there's a slightly, but yeah, it's totally explicit, right? Like, the thing. No, but in all these cases, we give some concrete way of kind of using the properties of that class and its complete problems to extract bad inputs. Yeah. Yeah. Right. So. Right, so let me give one example of like one of these kind of old lower bounds that we've known for a long time. They rely on information theoretic arguments. Making them constructive would give a major breakthrough in lower bounds. So there's a old result of Moss from 1984 showing that the language of palindromes cannot be solved by non-deterministic one-tape Turing machines in little o of n squared time. Okay, and this really exploits like the fact it's a Turing machine. You think you check a palindrome, you got to check, okay, the first symbol equals the last symbol and so on. Okay, you're dragging back and forth, and because of this, you're taking n squared. Okay, and even with non-determinism, it doesn't really help. But it's really information type theoretic argument to show that like what is a bad palindrome. You just pick one at random, roughly. You pick like the first half at random and then duplicate the second half, roughly. Is how you get it. Making this thing p constructive, or even making it p to the np constructive. So p to the np makes sense because it's a non-deterministic machine. So I feel like, okay, I need to give it np power to construct a bad input. This would imply a major breakthrough. So p constructive implies that exponential time has functions of exponential circuit complexity. Okay, from the famous work of Impalios and Vigderson from 97, this would imply universal de-randomization. P equals BB, like any randomized algorithm can be de-randomized. Okay, if you got P to the NP constructed, that would be exponential time with the NP oracle has these functions, and that would actually also be a breakthrough. It would show that randomized polynomial time can be simulated in polynomial time with the NP oracle. So very long-standing open problem. Okay, so this lower bound we've known for decades, but actually getting our hands on bad inputs with an algorithm seems very hard to do. So the upshot of all this is that constructivity is a property we want of lower bounds. It can be harder to achieve than what we know, but it seems to be like a big dividing line between what we kind of know how to prove and what we'd really like to prove. Right. So to give a couple more examples of like this phenomenon, because we have quite a few in the paper. So another example is like randomized streaming algorithm lower bounds. So there's many lower bounds for like streaming algorithms. We just pass along the input in one pass. You toss coins, and you give an answer. So many problems, including like simple ones like disjointness, where I give you the description of one set, and I give you a description of another set. You're supposed to pass it through and tell me whether the two sets are disjoint. So these things are well known to require like linear space randomized streaming algorithms. You basically have to store the whole first set to figure out disjointness of the second. Okay, so what we show is a pretty sweeping theorem about getting constructive separations for streaming algorithms. So take any problem in NP. Okay, so like that includes like P, that includes like log space, things like this, like things like so like right in the offline setting, disjointness is like in log space or whatever. Like I can move back and forth and figure out the answer. So for any problem in P, if you get a P to the NP constructive separation of this problem pi from even super logarithmic space randomized streaming algorithms, this would imply like a big breakthrough in lower bounds. It would imply that exponential time with an NP oracle is not equal to BBB. It's one of these embarrassing open problems we still don't know how to resolve. But yeah, like there are many problems, like even like disjointness, for example, where we know linear space lower bounds. So we know that the bad inputs exist for randomized streaming algorithms. but being able to construct them, even if I just get a separate algorithm for each input. So like I have a non-constructive way, say, of specifying the algorithm which prints bad inputs for a streaming algorithm. That would be a major advance. So another example is even for randomized query lower bounds. So there's this problem known as the coin problem. It's often called promise majority. So you have some epsilon, and you want to distinguish bit strings that have greater than half plus epsilon ones from strings which have strictly less than half minus epsilon ones. Okay, and you're allowed randomness. So you're crucially allowed random sampling. Okay, so with random sampling, I mean, you can do it in order 1 over epsilon squared queries, and it takes that many. Okay, I mean, if you only had deterministic things, this would take like omega n. But so with randomness, you can distinguish between the two cases with high probability and take only 1 over epsilon squared queries by just taking like a really large random sample and checking its number of ones. Okay. All right. Now this promise majority thing, it actually has pretty low circuit complexity. It's been known since the 80s to have actually AC0, these constant depth circuits over or an AND. So what we show is that an AC0 constructive separation. So if you had AC0 circuits that can print bad examples for like randomized query algorithms. So you give me a randomized query algorithm, and then I construct an AC0 circuit that is printing a bad example for this query algorithm. If you can do that, then P different from NP. So these are just randomized query algorithms that use too few queries, right? They use too few queries, and they use like poly 1 over epsilon time. So they use way too few queries to get the right answer. So there are bad inputs for them. Okay. The question is, how efficiently can you construct bad inputs for a randomized query algorithm? If you can do it in AC0, which is enough resources to check promise majority. If you can do it in AC0, then P is different from NP. Now, I'm not saying this is a way to prove P different from NP. I'm just saying that so somehow, right? This is the kind of argument where you really are using like some kind of non-constructive aspect, some kind of counting type argument, some kind of probabilistic argument, and making it constructive. Like you could, if you made it, slightly less constructive, it wasn't AC0 circuits, but it was like log depth circuits, you would prove P different from P space. I just took like the most like extreme example, which could still plausibly hold. And so I could say P different from P at the end. There's like a whole bunch of other theorems like this in the paper. Where like these lower bounds, which are like, from information theoretic probabilistic type arguments, if you can like get your hands on bad inputs with in an algorithmic way, then you would prove like a major separation. Okay. So now let me try to tell you first how to generalize this GST theorem. So how would you get a constructive separation of P different from P space? Okay, so we saw how to do it for P different from NP. So the theorem is if P isn't from P space, then there's a P constructive separation of P from P space. So in fact, we'll be proving it for a true quantified Boolean formulas that there's a P constructive separation that this quantified Boolean formula problem is not NP. Okay, so the proof idea, the first idea, is that instead of SAT, look at QBF. Now, I want to say like we generalize this stuff so much in the paper that I actually don't think this argument's anymore in the paper. This is like the first argument I came up, but like if you don't see this in the paper, I'm sorry. If it's like I think it's way more abstract than it used to be. But okay. But anyway, this is the way I was thinking about it. So we want to get a refuter for a polynomial time algorithm that's trying to decide TQBF. Okay. All right. So we're going to try to construct a formula that is trying to find bad examples, but we have to be careful here because we don't have like an efficient proof that a QBF is true or false. So we have to think of like somewhat differently about like what this counterexample formula is going to look like. So here's the idea. We want to say that there exists a QBF. Okay, it has some leading quantifier, right? So this quantifier is either exists or for all. Okay, G is some rest of the QBF. So you think of the QBF as being like pre-next normal form. So all the quantifiers are put first, and then the formula is given. Okay, so this is just the first quantifier in some QBF, and the rest of it's G. The whole thing is of length n. Okay, so there's some QBF where the following thing happens. Either A is reporting the wrong answer for all x, g of x, right? That will happen if the quantifier is for all. So for all x, g of x, it should be the same value as when I plug in 0 and when I plug in 1, right? Like this should be reporting the same value, because that's what for all means, right? Like, right, it should be true when both set to 0 and set to 1, okay? But I'm saying, okay, either that happens, like either there's a for all quantifier and this doesn't hold, or there's an exist quantifier, and somehow when I plug in 0, I plug in 1, it's still like it's not the same value. So let's say I declare this to be false, but like one of these turns out to be true, right? I mean, maybe the best way to think about this is think of the complement. Like if my A actually solved QBF, then for every QBF, it would report like if it would give me this equality for alls at the beginning, and it would give me this equality for exist at the beginning. And moreover, if any algorithm which has this property would just solve QBF, right? Like I could just use it to solve QBF, okay? To decide QBF. Okay, so it's like a inductive way of defining what it means to solve a QBF. Okay. And of course, like on constant size formulas, it needs to give the correct answer too. So yeah, but so the idea is that A is consistent on these on these three. So it's either these three formulas, depending on the quantifier, or these three formulas. It's inconsistent. It's not giving the right answer on at least one of them. So it's now we're in the same cases we were before with SAT, like where it was reporting SAT, but like the two when I plugged in 0 and 1 were unsat. But it's more general now. Okay. But the case is split just as before. So this thing declares, let's say, false. Okay, then we output the thing. Okay. So either we find such a QBF, or we don't. Okay. So if we don't find it, we just output that as this is like the counterexample of formula. Otherwise, we find such a formula. Okay. But if we find such a formula, then one of these formulas must be wrong. One of these three must be wrong, because they can't all be correct simultaneously to satisfy the semantics of QBF. So you can report the set of them as bad, or you can modify the refuter so that only one of these is reported, and then infinitely often you'll get a counterexample. Okay, so yeah, it's a bit weird. It's using like what it's using here is the downward self-reducibility of QBF. That like to solve QBF, I just need to call QBF twice on two smaller instances of QBF, right? One where I plugged in 0, one where I plugged in 1. And to solve QBF, I just need to like call it twice and then get back the answer. So to generalize this, as we do in the paper, you just need some kind of downward self-reduction. But yeah, that's the idea. So it's kind of bizarre that like you can still generate these counter examples, even though like there's no actual proof. Like you wouldn't be able to prove like which of these is true or false necessarily. You just know that there's counter examples there. Does this make sense? Okay.
Yes.
All right. All right. So now I'm going to talk about like making lower bounds constructive. What are the consequences of making lower bounds constructive? And so I'm going to sketch the proof that making the palindromes lower bound P constructive implies that exponential time has functions of high survey complexity. Okay. So this is showing that, or even P to the NP constructive, they get into the E to the NP has functions of high survey complexity. So somehow like the information theoretic counting arguments here like seems very hard to like get bad palindromes for an algorithm. So the way this works is actually going to be pretty direct. What we're going to do is we're going to make a single non-deterministic one tape Turing machine that takes less than quadratic time. So we'll just set epsilon to be sufficiently small into 1 plus order epsilon time. And it's going to correctly decide all palindromes of length capital N. So we think of capital N as a power of 2. So that way we can talk about it having circuit complexity less than 2 to the epsilon N. So now we're thinking of a palindrome as a truth table, okay? And we're saying like these are truth tables of low circuit complexity. So this non-deterministic Turing machine, when you give it a palindrome, like when thought of as a truth table, it has low circuit complexity, it will actually solve palindromes. So the point is that like if you give me an algorithm which can actually print a bad input for this, it must be printing the truth table of a hard function. Okay, so the point is, because we know a quadratic time lower bound, this one-tape Turing machine must make mistakes, right? It cannot correctly decide all palindromes. So there must be some palindromes, right, on which it doesn't. It says no, okay, but that must be a hard function because every palindrome that has a efficient description would have been decided. Right? So this is like an example of like getting a bad input for a fast Turing machine actually means you must get a hard function. Okay, so then once you've got your hands on a hard function like this, then this implies that exponential time has functions of high circuit complexity, because the idea is you give me n in binary, and then I write 1 to the n in polynomial time, and then I print this thing in polynomial time in n, but n was in binary. So it's just like a padding argument to show that this E has functions of high circuit complexity from here. Okay, so how does this one-tape Turing machine work? So if it has like a low complexity string, it will run in subquadratic time. All right. So here's the idea. So it's a non-deterministic machine. So the idea is to just simply guess a small circuit that encodes the input. Okay. So you guess a circuit of size into the epsilon encoding this input, and you guess the length of the input. Okay. So then it's a one-tape machine. But if you have a circuit of size into the epsilon, you can just kind of drag along the description as you read the bits. Like this, I'll take polynomial into the epsilon time to keep dragging along the description as you read the bits, like increasing the alphabet size and all that to encode the description as well as x. So you verify the truth table equals x. So you just drag along this description and verify that the truth table of this circuit, as I plug in different assignments, it actually equals my input. Okay. Now, once I've done that, I got a circuit. So the point is, once I've got a circuit encoding the whole input, I don't have to sweep back and forth like I would, in a hard input for a one-tape Turing machine trying to decide palindromes. I can just query the circuit to figure out whether it's a palindrome. So to verify whether X is a palindrome, I can just use a circuit. So what I do is I query the circuit, on various bits. Like I query it on like the index for the first bit and check that it's the same as the index of the last bit. And I know the length of X, so I know what the last bit's supposed to be. So I know what that index is. So like I can just, query the circuit on different pairs to check that it actually is a palindrome without sweeping back and forth. Okay. And if the circuit is sized into the epsilon, that will take into the order epsilon time to do. Okay. Just the usual simulation of like whatever algorithm you got on one-tape Turing machines is polynomial time. Okay. So use this to check the bits of the second half equal to the first half. To check that the length is correct, or you can just use a counter. You use a counter to check that the length you guess is correct. But that's it. So the point is, okay, here's a fixed non-deterministic machine. We know it cannot decide palindromes. Okay, can you, in polynomial time or even p to the np, construct a bad input for it? If you can, you've proved a major breakthrough in circuit complexity. And so that's what's going on here. Any questions about that? I know it's getting a bit late, and we've been going for a long time. So.
Sure. I have a quick question.
Sure.
Essentially what you are doing here, you are essentially thinking of a circuit as just as a model of an algorithm for encoding information about X in a smaller string. So
Yeah,
could you work here with some more general notion of Kolmogorov complexity or something like that?
absolutely, absolutely. Yeah, yeah. I mean, yeah, you could get some. So what we want is a random access version of Kolmogorov complexity, kind of.
Yeah.
And this is like min capital K capital T complexity, but this really corresponds to circuit complexity. But yeah, that's what you want. It's like a random access version.
Yeah. So the circuit complexity is here a complete model.
Would that work for copy instead of PAL? I mean, it works for. Actually, this is a very special case of a much more general statement. It works for basically any problem in non-deterministic linear random access machine time. Actually, so yes. I'm not even sure what copy is. Just you repeat the same thing, right?
Yeah, WW. The thing with copy is that the complement of copy is much easier than copy itself.
Yeah. It certainly works for copy. It works in much more generality than what I put here. I just put like a very simple case to make it easier to understand after like 2.5 hours or whatever. Right. Yeah. There's much more general thing.
Yeah, the main trick is clearly that you have you need to pass order of an information through the.
Yeah. So the point is that like if you've got this communication complexity bottleneck, then the bottleneck disappears if you are working with low circuit complexity inputs. Yeah. So right. So I guess I have 2 more slides.
I think we have like 8 more minutes according to the schedule.
Okay.
So, yeah.
All right. I mean, okay. So I'll say a bit about the next to last slide then. So I just want to say a bit about like this these query lower bounds. So recall we had this promise majority thing. If my PowerPoint worked there. Yeah, so we're distinguishing bit strings that have it greater than half plus epsilon fraction of ones from strings with less than half minus epsilon fraction of ones. And you can use randomness, and it's crucial to do that. So it's folklore to show that, say, if you want a high probability answer, you want to get the correct answer with 99% probability, you need 1 over epsilon squared queries, so omega of that, and that's sufficient. And like one way of looking at this, like making this lower bound NC1 constructive, so like log depth circuits constructive, implies P-ism from P space. Okay, so having log depth circuits, which can solve even majority, they can compute majority exactly. If they can find bad examples for a randomized query algorithm, you would actually separate P from P space. So this is certainly enough to compute promise majority, even exact majority. And the question is, like, can you construct these bad inputs for query algorithms? So let me just give a sketch of how this thing works, or the idea. So the idea is that P equals P space has a lot of interesting consequences to it. P equals P space, roughly speaking, it says that if I had like a log depth circuit printing an input, this log depth circuit must be like whatever output it prints, it actually has low circuit complexity. This is something we can kind of say. So we can correctly compute promise majority using poly log n over epsilon queries. So we think of epsilon as being small enough that this is much less on every string printed by some NC1 circuit. So uniform NC1 just means that like I can tell you what any particular gate is and how they're wired together like very efficiently. There's like a locally efficient way of describing them. So first, like if P equals P space, then like every such X printed by such a thing has like a small size circuit encoding it. So it is kind of similar to the previous argument that like the input is going to be shrunk whenever the input's being printed in a certain way. Okay, so this X represents a truth table of the circuit. So our input is now the truth table of the circuit. And if P equals P space, then you can do, roughly speaking, you can do pack learning on a circuit. So So a good approximation to a circuit can be learned with a small number of randomized queries to the input. Okay, so if P equals P space, then by just sort of probing the input in various places, you can get actually a good approximation. So you can get a good approximation in since you can get a string which is close to the input string in terms of Hamming distance. So it's actually pretty, its number of ones is going to be pretty close to the number of ones in the input string. But if you've got that, then you can compute promise majority. So the idea is that you can determine promise majority for such X with fewer queries. So the idea is we can use, if P equals P space, you can use like a learning algorithm on the input X. And this X is a small representation, so it can be efficiently learned under P equals P space, but then you actually get like fewer queries. So this is just like the contrapositive, saying if P equals P space, then the kind of outputs printed by every log depth circuit is actually going to be computable efficiently with promise majority. So it cannot refute in any algorithm like this. Okay, so there's learning theory stuff going on, and there's all kinds of wild stuff going on in this paper, like connections to these problems. Yeah. So yeah, let me just finish up. So here are like the big questions I think remaining. So relativization has told us for many years that direct diagonalization-based proof methods are limited. Okay, but like any major separation against P or BBP or ZBP is going to require a key property of diagonalization-based proofs, namely this ability to efficiently produce bad inputs. So the question is, what other methods of proof could let you print bad inputs? Okay. Yeah, I mean, like, because we know direct diagonalization-based proofs cannot work because of realization, but nevertheless, you got to print bad inputs. Your proof method has to allow that. So this is a big question, like, what else can you do? So what about separations against log space in C, ACC0? Like we're just talking about polynomial time. So yeah, I mean, generalizing this to other classes is interesting too. And then finally, right, there is some connection, it seems, between circuit lower bounds and these constructive separations for information theoretic stuff. Maybe there's an equivalence. Maybe what we're looking at is a de-randomization problem in disguise. Like it's just the same problem. I don't know. All right. Thank you for your attention. Thanks for hanging around for so long. I hope you got something out of
Yeah. Thanks a lot. I've learned at least a lot. I hope that many people are around also. So I think that within like a 3, 2, 1, we can unmute ourselves and applaud Ryan for this amazing
Right.
stuff. So 3, 2, 1. Yeah, that was great. So any questions regarding any more technical material, or I guess this is also now a good moment to ask some more general, let's say, questions.
Are we doing chat or with the mic?
I think we can just unmute ourselves and ask. Just do it so that we don't speak 3 of us at the same time.
We'll give it a try. I hope a simple one. Are all the proofs for the first part of the statement all relying on downward self-reduction?
Well, so beyond P space, they can't, right? Because if you have a downward polynomial time downward self-reduction for like a problem, then it is in P space. So beyond that, they use other reducibility properties. I mean, it's hard to I think summarize succinctly, but yeah, you have to go beyond downward self-reducibility. I just want to choose that one because it's like kind of the cleanest to talk about. But yeah, I mean, there's other tricks involved, but basically, yeah, you exploit properties of complete problems for these classes, like X and so on. But yeah, up to p space, you can do these kind of things.
Makes sense. Thank you so much.
Yeah, Damian, you have a
Yeah,
question?
well, general question, do you take into consideration that maybe the claim is independent of set theory axioms? Yes.
Oh,
Because
that like P from MP is independent of set
mhm.
theory.
Is
Yeah,
there, I think it's a possibility.
I don't know. I mean, I don't have I don't really have good reason to believe that it I don't know, has some like that it is such a rich statement that that the independence would be hiding in it. Yeah, I mean, I just think that somehow it's a question that is very general, but is it's kind of laser focused on a particular type of computation, and that makes it difficult to distinguish between P and MP. Like at least in terms of like the techniques we have used, the techniques we have used are kind of too crude to kind of cut them, or even maybe show that they're the same. But yeah, I don't have any. I don't think that they're independent. Yeah. I just think
Maybe
they're
we
very
could actually try to prove that it cannot be independent, but that's
yeah. Yeah. Short of resolving the thing, I'm not sure how to do that. But that's an interesting question. Like, could you show it can't be that it must have a resolution one way or another? Yeah, I'm not sure, but yeah, my intuition is that these problems can be resolved, and it's just we're just lacking a lot of tools. Yeah.
I see another question of Mikael.
Yeah, I don't want to monopolize the question time, but I saw there was a raise hand feature on Zoom. I wanted to try it.
Yeah, we can try to do it. So if any other people have questions, maybe you can raise your hand so that I see what's going on. Yeah.
Splendid. And as the host, you can lower the hands of people. You only mentioned uniform classes, right? Is there something specific about non-uniform classes that don't allow the kind of results?
Oh, you mean like right, like can we expect some kind of constructive separation of MP not MP poly, and what would that mean?
Mhm.
Right. So yeah, this is a good question. So there definitely some, like, we were definitely just focused on uniformity because it was easier to reason about. I mean, at Sirius has some version of so Albert at Sirius has some version of the GST result, which works for p-poly. But it works in like a black box-ish type way. And it, like, I don't really know how to describe it, but like it's somewhat different, to say the least. It's a different approach, and I am not sure how we would generalize that. But yeah, I think that's a good question to think about, like the non-uniform versions of these things, like, I don't know, p-space not in p-poly and stuff.
Cool. Thank you very much.
Yeah. Thanks for the question. That's a good question.
Yeah, I've got a question as well. All of the stuff that you were talking about was around P, roughly. And I was wondering all the way, and actually touched upon it on the very last slide, what about log space? Because for me, at least, like, log space machines are the like sort of simplest Turing machines that you can still have this Turing machine flavor. Is there any like what can you say about the distinguishment of proving lower bounds against around P and around log space? Is there anything simpler about log space that one can exploit?
Well, I mean, like I alluded to this, I don't know, a couple hours ago or something, but like, yeah. So like with log space, there is definitely more you can exploit. And so there are lower bounds which directly exploit like the small space of the machine. But like, I guess if you look at the arguments that we had for like say the proof of the GST theorem. Like we run this algorithm, we get back a formula, and then like we check that it works, and then we like we either reported this other thing. I mean, I suppose like yes, I guess it's like this probably could be carried out in log space, but yeah, I'm not sure like if
You run into technical problems.
I think so. Yeah. I mean, it's not obvious because we're taking like the output of one thing and then running on something else. And yeah, you can compose log space reductions, but it blows up the running time considerably. And it, yeah, it's a bit strange. But yeah, like, so there are these like proofs based on like indirect diagonalization that like SAT is not into the 1.8 time with log space. And yeah, I mean, in fact, like you can generalize that to in various ways. So for example, like if you allow the small space algorithm to use like also a little bit of advice, like in a non-uniform sense, like into the epsilon bits of advice on inputs of LinkedIn, you can also prove this lower bound. And what we showed, I mean, this stuff about randomized streaming algorithms essentially implies that making those lower bounds constructive actually would imply a circuit lower bound. So even though these are proved by indirect diagonalization, we don't have ways of constructing bad inputs for them. So like indirect diagonalization means that like you assume the opposite was true, and then you apply that thing many times, and then somehow you got a contradiction. It's not clear how you get a bad input from this process. Yeah. Yeah.
Okay, I see that Mikael has another question.
Yeah, so you insisted a few times on the weirdness of the fact that your algorithm for majority for what was that? Something majority. What was the adjective yet before majority?
Are you talking about palindromes or?
No. So what was that from promise majority? Sorry, for promise majority. Thanks for someone in the chat who sent me a PM for
this
that.
This thing here.
Yeah. Yeah, so you insisted that it's weird in some sense that this algorithm can already solve promise majority, that it's in NC1 or in ACZ.
Well, I mean, if someone never saw it before, then maybe, yeah. I mean, I'm not, no, I mean, this is a standard result that a majority
No, sure.
Oh,
sure,
I was talking about when promise majority is in AC0, yeah.
Yeah, so you said it's a bit weird that you're looking at the NC1 constructive algorithm here, although the target is promise majority, which is even much lower than NC1. So is that it wasn't the case for the original theorem where we're looking at something that was polynomial time, right? And that couldn't solve SAT.
Yeah, this is a different kind of thing, right? So this is like from the second class of results.
Sure.
Right. In the first, right. So like the first class is saying if this there's a constructive thing. This one's saying we know the separation holds, but making it constructive implies P different from P space.
Yeah, I understand. Yeah. It's just I don't know. It seems this NC1 constructive, while the target problem is in AC0 is, I don't know. You seem to insist on that a few times. It was strange that we were able to solve the problem. Within,
I don't know. I mean, maybe I think I meant strange in a different way from what you're thinking. Yeah, like maybe I was saying it was strange that it already implies P different from MP and P different from P space, like based on the thing. I mean, like that's but no, is so like clearly you can compute the answer, like you can check your answer with an NC1 circuit. Yeah, I don't know. I'm not sure exactly what I called weird, but I didn't mean to say that it was weird. You can compute it. I don't know. I think it was weird that it already implies P different from P space or P different from MP.
Okay, let me give it one last try.
Okay.
If we had one refuter for SAT that could actually compute SAT, would it make things simpler?
If we had one refuter for SAT that could actually
Only have the
compute
power. Yeah.
SAT, well, then it wouldn't be a polynomial time refuter, would it?
No.
Like if we're assuming P from MP, right?
Yeah.
Polynomial time refuter cannot solve SAT by itself. It can only, be lucky infinitely often and report like things which are satisfiable.
Right. So you would have an NP refuter for SAT.
Or
And
a P time refuter. Yeah, given
then,
P is in from MP.
well, what if you had an NP time refuter for
Okay.
SAT, for P time algorithms for SAT?
Okay.
Right. So you would have more power in your refuter. It could actually check whether some formulas are satisfiable or not.
Yeah.
And does that help you in any way to have more power in the refuter, just like you have more power for promised majority?
I see. So well, yeah, let me try to understand. So if P is in from MP, we know that there are P refuters. You're saying like, could we prove that there's, I don't know, like, well, I guess there is a P to the MP refuter for any algorithm. Like it just, I guess.
That is I think that's the bottom of my question.
That just holds.
Yeah. If I have an NP refuter for SAT, does that show anything?
Yeah. I don't know. I mean, I don't know if this is yeah, I mean, I think I don't know if it shows anything. So yeah, I mean, like to get P to the MP refuters to imply something interesting, it needs to like start from some lower bound that we know, right? And we want to make it constructive. So because we want to make sure that the bad inputs exist, and then say, oh, okay, getting them in P to the MP actually implies something. It means you constructed some input with interesting properties. Maybe it turns out to be a hard function or something like that. Yeah.
That was a satisfying answer. Thank you.
Okay.
And
thanks for yeah, probably the best I can do
hard.
after this. After
That's right. Thanks for working hard to understanding this. Thank you.
Yeah. Do we have any last quick question? Doesn't seem so. So yes, thanks again, Ryan, for this great talk. We can all clap in the chat to show this. And I guess that at the end, there is a quick announcement from the organizers, so Wojtek or Filip.
Yeah, thanks. So, well, first of all, thanks again, Ryan, and thanks, Michał, for the amazing job. I just wanted to announce that, well, in 2 months, in April, I think 1st of April, we will have not only Majesh, she will talk about the algebraic version of P versus NP. And I'll send them detailed email next week. So thanks again.
Yeah.
Thanks for inviting me. Yeah.
Yeah.
It was
so
a good exercise to try to collect my thoughts. Yeah.
Yeah, it's amazing. I've learned so much today.
Good,
Yeah.
good,
So
good.
I guess that we all can be happy and have a nice rest during the weekend.
Yeah. I'm switching my water to beer. Yeah.
Yeah, we should do that here as well.
If I did that for 3 hours, I would definitely not give a lucid type. Okay.
Okay. Yeah. So thanks a lot, and hope to see you next time.
Yeah. Thank you all much. Prost.
See you. Bye.
Bye.